In this video, we're going to put everything that we've learned in the previous videos into practice and do some coding using Python in TensorFlow. This might seem overwhelming at first, but as you look at the code again and again, it'll start to make sense. Programming CNNs is a bit of a skill that you'll learn in hours of practice and tweaking your model again and again. So let's get started. We'll look into setting up our variables before making the actual CNN graph. Then we'll set up our model for the CNN. And after that, we'll create a session in which our network is going to be trained. The code architecture is very similar to the previous section code. The main thing to be changed here is the model, in which we're going to be adding some convolutional layers before the fully connected network layers. You can see the 3 fully connected convolutional layers weights and biases in the dictionary. We almost always use square patches on the inputs, i.e. with the same width and height. Here the num underscore of underscore channels variable. Here the num underscore of underscore channels variable tells how much the depth should be of the convolving kernel, and the last input shows the depth of the output kernel layer. In other words, because we're going to extract a bunch of features from this image layer, we specify how many kernels we want to have in the last input of the vector. Also, here the fc underscore first underscore layer underscore dimen function calculates the number of inputs features coming out of the layer network layer based on the image size and number of convolutional layers in the network. The depth underscore inc variable shows how many features we're going to extract at each convolutional layer. Now in the model portion of our code, we have implemented a smaller subset of the AlexNet. In other words, a smaller lookalike of AlexNet. AlexNet is a big network with millions of parameters, so we're going to implement a smaller version of it. We have a low number of classes, and most of you guys will have only CPU to compute on. As AlexNet could take up to days or even weeks even on GPU, we've decided to go with this model approach. So here, we basically have 3 convolutional layers as discussed. And after that, we have 2 fully connected layers to get the final output in a reasonable format. In between the convolutional layers, you could see the discussed pooling layers with the strides that we talked about previously. The type of pooling that we use here is max pooling, and the type of padding we use here in the convolutions is the same padding. Also, you could see a dropout layer in between the fully connected layer and last convolutional layer. The fully connected network code is in the next slide. This is basically a regularization technique that helps in getting better test accuracies. We won't go into much detail of this. Just be careful that dropout is only meant to be used during training phase and not in the test phase or finding accuracies. That's why we've added a boolean that tells to indicate if it's in the training phase or not, in order to decide whether dropout should be used. Here we're going to unwrap the convolutional layer output to be linearly presented to the fully connected layer as a 2D matrix. For now, we're going to treat the incoming inputs as a single image, as we did in the case of fully connected networks. The difference here is that each input of the incoming matrix is a feature extracted before in the previous layers, and this acts as a better way to handle the information contained in the image. Finally, all the computation that we've done here is returned from this function. So now's the time to structure our models, combined with the different inputs that we're going to have to give to it. Here we've combined the network with a softmax function to calculate the probabilities, and in the same step, we've also added a loss function to calculate the loss. Lastly, we've calculated predictions of the outputs based on the different input sets that we have. Here, we've added train many batches prediction, validation set prediction, test set prediction, and for evaluation purposes on new data. Later on, we've added a placeholder model for new images. Great job, guys! You've implemented your very own first convolutional neural network. We've learned where to put everything to have a working CNN, and how we've used the previous fully connected code architecture to incorporate the new changes. Try to run this code and let it train for a while, and just see the magic happen. We've trained this network on a new dataset, i.e. CIFAR 10 dataset. In this dataset, we have different images of cats, dogs, cars, aeroplanes, etc. Now, you could have a neural network trained to identify the images of cats and dogs. That's exciting, isn't it? In the next video of this section, we're going to have a look at what TensorBoard has for us to visualize using the code that we just wrote. Good luck!